Application of DSC. Thermal methods are multi-component techniques and include thermogravimetric analysis (TGA), thermogravimetric analysis with evolved case analysis (TGEGA), differential scanning calorimetry (DSC), thermomechanical analysis (TMA), dynamic mechanical analysis (DMA). These methods find widespread use in both quality control and research applications on industrial products such as polymers, pharmaceuticals, metals, and alloys. In this video, we will discuss applications of DSC. Now, what is DSC? In DSC, the difference in the amount of heat required to increase the temperature of a sample and reference is measured as a function of temperature. So, in DSC, energy is applied in the form of heat, and that energy is used to be measured. The provision of energy in the form of heat must be at controlled rate. The exothermic process releases heat while endothermic reactions absorb heat. Examples of exothermic reactions are crystallization, curing, and oxidation, whereas examples of endothermic reactions are dissolution, melting, glass transition, and decomposition. DSC is the most commonly used thermal analysis technique in pharmaceuticals. These are some applications we will discuss one by one in this technique. Number first, amorphous versus crystalline sucrose. Heat, cool, reheat cycle to study the thermal nature of the thermoplastic polymer. Enthalpy of fusion, calculation of person crystallinity, and melting point. Thermogram B represent crystalline sucrose. Here we have no glass transition as the materials are crystalline and the melting point is sharp below 200 degrees centigrade. We can see here. On this slide, we have heat, cool, reheat cycle to study the thermal nature of thermoplastic polymer. There are two types of polymers commonly used in pharmaceutical packaging. Number first, thermoplastics, and number second, thermosets. A thermoplastic is any plastic material which melts into a soft, pliable means flexible form above a certain temperature and solidifies upon heating. Common examples of thermoplastics include acrylic, polyester, polypropylene, polystyrene, nylon, and Teflon. This type of plastic is common for making plastic containers, whereas thermosets are often preferred for sealed products because they offer structural integrity and superior heat resistance. They are often used to create protective layering for other packaging materials as closure lids for glass and plastic packaging, as durable pharmaceutical casings, and more. The most frequently used thermoset plastics include melamine formaldehyde, epoxy resins, phenol formaldehyde. In first heat cycle, shown as a blue line, we have glass transition followed by crystallization and melting peaks. In short, first thermogram is a function of the material and an unknown thermal history. After first heating cycle, the material is cooled at a controlled rate, shown here as a red line. The cooling segment data provides information on the crystallization properties of the crystallizable polymer and gives the sample a known thermal history. In the second heat cycle, shown as a green line here we have no glass transition crystallization. The only peak showed by material is melting. So the second heat data is a function of the material with a known thermal history. The third application of DSC is determination of enthalpy of fusion. What is enthalpy of fusion? Enthalpy of fusion of a substance, also known as latent heat of fusion, is the change in its enthalpy resulting from providing energy, typically heat, to a specific quantity of the substance to change its state from a solid to a liquid at constant pressure. The enthalpy of fusion, represented by HF, is obtained from the area of the endothermic transition. We can see here the shaded area in thermogram. The enthalpy of fusion of this sample is 28.87 joule per kg. The unit of enthalpy of fusion is joule per kg. Another application of DSC, that is calculation of person crystallinity. What is crystallinity? Crystallinity refers to the degree of structural order in a solid. In a crystal, the atoms or molecules are arranged in a regular periodic manner. Now the question is why the degree of crystallinity is important. A simple answer to the question is it influences the hardness, density, and transparency of materials. Moreover, it defines stability and drug release properties of the final dosage forms. For calculating the person crystallinity, we must know enthalpy of melting for 100% crystalline materials, that is delta H in literature. For standard samples, person crystallinity can be calculated by dividing the enthalpy of melting of the sample by enthalpy of melting in the literature multiplied by 100. For samples with cold crystallization, the person crystallinity is measured by subtracting the enthalpy of cold crystallization from enthalpy of melting of a substance divided by enthalpy of melting of the same substance in the literature multiplied by 100. This is the DSC thermogram of polyolefins. The person crystallinity is 49%. 290 is the enthalpy of melting of polyolefin in the literature. This is another application of DSC, that is melting point. What is melting point? Melting point is a fundamental physical property that specifies the transition temperature between solid and is widely used in pharmaceutical sciences, organic chemistry, and biological chemistry. For example, it is used for compound characterization as well as purity evaluation in organic chemistry and also as a descriptor for the prediction of solubility, a key determinant of the bioavailability and in vivo activity of a candidate drug. For accurate determination of melting point, DSC mean differential scanning calorimetry is used. Here we have T naught is the onset to melting, Tp is the melting peak temperature, Te is the end of melting. Pure low molecular weight materials having molecular weight less than 500 gram per mole. T naught is used as the melting temperature. Between T naught and Tp, the sample is melting. Between Tp and Te, the molten sample is returning to the DSC temperature. For polymers, broad melting peak due to crystals with different degree of perfection. Tp is used as the melting temperature. Melting and further perfectioning can occur simultaneously. For pure low molecular weight materials, the molecular weight less than 500 gram per mole, we use extrapolated onset as melting temperature. Here on this slide, we have the extrapolated onset temperature is 156.60 degrees centigrade and the peak temperature is 157.01 degrees centigrade. For polymers, use peak as melting temperature. Here on this slide, we have peak temperature is 249.70 degrees centigrade.